What I want to do in probably the next half an hour, 35 minutes to give us time for questions is talk about essentially, actually, I'm going to do what I really hate when speakers do at events like this, which is that I'm going to tell you all about the fun that I've been having in astronomy. Now, of course, the worst version of this is the observational amateur astronomer who tends to start talks by saying, when I was in Hawaii, and when I was at the Very Large Telescope in the Atacama Desert, but at least my work mostly involves sitting in front of a laptop. And it's done collaboratively with many millions of people now. So I want you to think that I'm speaking for everyone who could get involved rather than just talking about things I did on my holidays. It's actually funny to have started with those beautiful pictures of comet Neowise, because for me, astronomy starts by looking up at the night sky, looking at a horizon like this one. I've pulled out, this is an old copy of mine of The Story of the Heavens by Robert Ball. So this is, I think, was published in the year 1900. It's actually somebody's school prize from 1901. And I really, really like, I don't know if you're going to be able to see this, I'll show it properly later, but this is in here, there is an illustration of the Great Comet of 1882. And what's amazing about this is it's got a very Neowise-like view of a comet with a long tail above a row of what look like sort of suburban houses. And I think that's been my experience of Neowise in the last few weeks. I haven't been able to get anywhere particularly dark or particularly rural to see it, but I have been wandering out into the neighbourhood in Oxford and finding gaps between neighbours' houses to see the comet. So looking at the sky is, I think, what grounds all of us in astronomy. And I think that's why clearly there are some excellent photographers in the group, but you know, why even an image taken with something as basic as a mobile phone has such resonance. It's a connection between you as an observer standing on a planet and the night sky. And you may look at this shot that I've got on screen and decide that it's not much at all. There's a horizon. Maybe if the connection's working and your screens are good, you can see there's an evening star in this sky, which is just after sunset. And if we zoom in, actually, you can see it's unusual. It's a double star. And it's double because this is, as some of you may have guessed, this is the view from Mars. This is an image from one of NASA's rovers taken back in 2014, 80 minutes after sunset. And that double star that you see in the evening sky is the Earth and the Moon. And so I think that by seeing this, I have much more of a sense of what it would be like to be on Mars than I would ever get from 1,000 color satellite images showing the amazing features of the red planet. There's something about standing there and looking at the night sky. And the first thing I want to say this evening is that how I view the night sky, how I think all of us should, has changed in the last couple of years. When we look at this gratuitously beautiful picture of the summer Milky Way, you can see obviously a smattering of stars. You can see clouds of gas and dust from which you can form more stars and more planets. But we now know what we didn't know even a few years ago, which is that most of the stars that you see here, most of the stars that you see in the night sky have planets going around them. And so I think probably it's worth saying that if you're a particular type of theoretical physicist, that's probably not very surprising. The same physics and the same chemistry that produced our solar system will have taken place across the rest of the universe. And so maybe it's not surprising the outcomes are similar. But for somebody who feels that connection to the night sky, I now look at this and think, or look at the night sky and think of all the worlds that we could be visiting. This is a map that shows us where we might be going. And I genuinely think this is a profound thing that's going to change how people feel about the sky. In the same way, perhaps, that getting the first images of the Earth from space changed how we feel about our planet. I can even show you some of those planets. So this is a star called HR 8799, as viewed from an instrument attached to the Very Large Telescope in Chile. Actually, most of the light from the star has been subtracted. The little yellow thing has been added back in. That's not what stars look like. And we've done that so you can see. I promise myself that I will never do that. I keep saying we when I mean astronomers. Clever people who aren't me have subtracted all of the light from this star, and the four blobs that you can see there are planets, and they move over time. So this is the course of several years worth of observations. And you can see this is a blown up version of our solar system with four planets in orbit around their star. And I love this because I've used this animation in almost every TV program about planets I've ever made. You've seen this a billion times, but this is real data. We now watch planets going around other stars. And so I think if you're interested in astronomy, and certainly if you're a professional astronomer right now, it's incumbent upon you to have a favorite system of planets, because this is the most exciting thing that's happening in astronomy right now. And my favorite system of planets is this one. It's called K2138, that's the name of the star. And at discovery, there were 5 known planets. So B, C, D, E, and F around the star. And luckily, they're in that order. But what's cool about this system are a few things. So one, this is to scale. And you can see F is about 10 million, a little more less than 10 million miles from the star. So all of these planets are crammed close to their star. So the best equivalent in our solar system might be something like the moons of Jupiter, the Galilean moons of Jupiter. Io, Ganymede, Europa, and Callisto are crammed close to Jupiter, just as these planets are crammed close to their star. But the second thing is that there's a pattern to these orbits. So B, the innermost planet, goes around the star in just 2.35 days, 2 1/3 days. So its year is 2 1/3 Earth days long. The next one out, C, goes round every 3.5 days. And actually, if you work this out precisely, it turns out that for every 3 orbits B completes, C goes round twice. And for every 3 orbits C completes, D goes round twice. And for every 3 orbits D completes, E goes round twice. And for every 3 orbits E completes, F goes round twice. So there's this pattern to them. It's called a harmonic series. And it tells us something about how these planets formed and evolved. In fact, it tells us that these planets formed, we think, a long way from their star. They migrated inwards, a process that we think is pretty common in some of the solar systems that we're finding, planetary systems, exoplanet systems, I guess. But it tells us that that process was calm and not chaotic, because the planets have found their way into this nice resonance. And because there's 5 of them, there aren't any gaps. There's no space in that series where we could put an extra planet. So this makes this system particularly exciting and interesting. I'm particularly excited because we heard just in the last day or so that this planetary system is going to be targeted by this spacecraft. This is an artist's representation of a spacecraft called Cheops, which is a small European Space Agency satellite. And it's the first satellite that's been launched to follow up on known planets. And it's going to do that by watching for transits. So the K2138 system is a system in which the planets happen to get in front of their star as seen from Earth. That's how they were discovered. People spotted the blinks that occurred in the star's brightness when these planets got in the way. But Cheops will do very precise timing of those transits. And the idea here is that the planets might be affecting one another. So the gravity of C might pull B, and depending on where they are in their orbit, B may be early or late in its orbit. And so by studying these effects, we can find out much more about these planets. We can find out something about their mass. Maybe we can find out about their structure. So this is an exciting system that you will be hearing more about in the next year or so. But it's exciting to me because it was discovered not by professional astronomers. We missed it, but by volunteers, citizen scientists, we call them, but amateur astronomers. Amongst them, this guy. This is Andrew Gray. He's Australian. He lives in Darwin, in northern Australia. And this is a shot from the interview he did the day after discovering 5 of these planets. His boss said that he could do interviews if he wore the company shirt and made them look good. So I need to tell you that if you need a BMW repaired in Darwin ever, I know a guy. But Andrew's great. He's an amateur astronomer most of the time. He has a a 14-inch Dob, I think. And in the interview, he was asked how he was going to celebrate. And he said he was going to take his telescope out that evening and have a beer with it, which is both lovely and very Australian. So Andrew didn't discover the planets with his Jobsonian, with his telescope, though. He visited a website that my team set up called Planet Hunters, which took data from NASA's Kepler satellite, which is a planet hunting satellite, responsible for most of the discoveries, and put it online for people to investigate, to look for these dips in brightness. And if you go to planethunters.org now, then you'll find data from NASA's TEST satellite, which is the new generation of planet hunting satellite. And just today, I got new data from the big Gemini telescopes, the 8-meter telescopes in Chile and in Hawaii, following up on discoveries made by people sitting in front of their web browser. So a Virtual Astronomy Club, I'm sure, has lots to contribute to the discovery of planets. So we've gone in 25 years from the discovery of a planet around another star being something that would win you the Nobel Prize to something that is now not routine, but where, in a sort of spirit of all hands to the pump, we need hundreds of thousands of people to sort through the data that we're obtaining to try and find planets. And really, the topic of this talk, the research that I do, is about connecting the worlds of professional and astronomy with amateur astronomers, astronomy societies, and people online around the world to try and make discoveries. It feels to me that this is partly something I've wanted to do for a very long time. I grew up as a small kid with a small telescope, going to Astronomical Society meetings, mostly at the Torbay Astronomical Society, and trying to think about making discoveries. I remember deciding that I wanted to discover a comet, because Comet Lintott, I still think, has got an excellent ring. It's much better than Comet Neowise as a name. And I'd more or less given up on that till I discovered recently that if you join the appropriate group at Queen's University Belfast, then you get the next comet off the production line. So I'm quite tempted to go back and start again. But I never discovered my comet. And on screen now is the closest I've come to making a discovery personally. Having given up really on making discoveries in the early 90s with a 6-inch reflector from a light polluted site in suburban Devon, I spent a lot of time staring at the Orion Nebula. I suspect lots of you on this call will know why that's worth doing. I always think that the M42, the Great Orion Nebula, is one of the few objects that to the eye, in my astrophotography, but to the eye through a telescope, really pays effort back. If you're properly dark adapted and the skies are clear, you see the three-dimensional structure of the nebula. So I've spent many hundreds of hours over the years looking at M42 and enjoying the sight. But this is what you see if you nudge the telescope and it moves. This is slightly to the north. You can see the nebulosity is to the south here. So that's the edge of the nebula. And you get this rather pretty cluster, which one evening I nudged the telescope, about 14, and this cluster swam into view. And I remember pulling a star atlas off the shelf and looking, and this cluster wasn't marked on it. And so I remember getting a pencil out and putting a cross and calling this Lintott 1. It wasn't until I got online the next day that I discovered this is in fact NGC 1981. It's perfectly well known. It was discovered about 150 years earlier. And really at that point, I think I thought I'd realized that discovery didn't happen like this anymore. Discovery, I thought I'd learned, came from big facilities. So as I grew up, got my PhD, I started to think about data from big surveys. So the reason I'm not standing on stage, well, apart from all the virtualness, but the reason I'm not sitting and going, oh yes, and when I went to Hawaii and when I went to Chile, I did this and so on, is that even observational astronomers these days get to collect data from their computers, because mostly we collaborate to use data from big surveys. So this is the Sloan Digital Sky Survey. It's a 2.4 meter telescope in the hills in New Mexico, place where they get about 320 clear nights a year. They're pretty picky about the definition of clear as well. And for 8 years, this telescope just allowed the sky to turn over it. It recorded the position of many hundreds of millions of objects. And amongst them, automatic routines identified 1 million fuzzy objects which were likely to be distant galaxies, the equivalents of our own Milky Way. And on the clearest nights, Sloan went back and used a spectrograph, one of the first decent fiber optic spectrographs, if that means anything to you, to record spectra of 1 million of these galaxies. And so that's how astronomers make discoveries. We use surveys, computers, we get the data, and then we can ask questions about our galaxies. So here are 2 galaxies. Looking at them, these are both from Sloan. I've cheated slightly by picking nearby ones, so they're more beautiful than the average blob contained within the survey. But just looking at them, you can see that there are differences between these 2 galaxies. And one of the things that never ceases to amuse me about astronomy is that we're very good at taking the beautiful wonders of the cosmos and reducing them to pretty prosaic numbers. So, for example, one of the differences between these 2 stars is the color. One of them is red and one of them is blue. Astronomy is often a simple science. The colors of the galaxies are different. They're different because they contain different types of stars. And in fact, what's happening here is that if you see a blue galaxy, that's because its light is mostly coming from very massive stars, big, bright OB stars specifically. And those stars don't hang around for very long. So they last after formation for maybe as little as 10 million, maybe 100 million years. And so just by measuring the color of these galaxies, I can tell you that the one on the left, I don't know if this is mirrored, the blue one has had star formation recently within the last 100 million years, and the other one hasn't. So the color of a galaxy tells you about what's happening there right now, because the last 100 million years is right now as far as galaxies are concerned. So what other information can we get from these galaxies? Well, the other thing you notice immediately is that they're different shapes. One is a beautiful spiral galaxy, just like our Milky Way is, and the other is a elliptical, a big ball of stars. And so the shape of a galaxy tells you about its long history. So everything that happens to a galaxy over the 13 and a bit billion years since the Big Bang, or whenever after that the galaxy started forming, the shape of a galaxy is changed. So every time the galaxy collides with a neighbor, eats a satellite galaxy, grabs material from its surroundings, has an active period of star formation, all of those things affect the shape of the galaxy. And so while color tells us about now, the shape of a galaxy tells us about its history, its past. And so we can see that these 2 galaxies have probably had very different experiences. But there's a subtle problem here, which is that if I want to know the color of one of these galaxies, it's not a very difficult measurement to make. I can just essentially put all the light in a single pixel and see what color it is. I can write a couple of lines of code that do that. If I want to know the shape of a galaxy, let's say I want to find all the spiral galaxies, that's a much harder task to automate. And so what we do instead is look at the images. This part of astrophysics is still a very visual science. Or at least that's what we used to do before things like the Sloan Digital Sky Survey, this monstrous beast of a telescope, came along, because Sloan suddenly overwhelmed the world's astronomers. If you were doing this sort of studies studying the 50s, 60s, 70s, or 80s, you would have a few hundred such galaxies to look at. Sloan provided 1 million, and so we gave it to a student to do. So the student's name was Kevin Szawinski. When I arrived in Oxford in 2006, he'd been set the task of classifying 50,000 of these galaxies. And for 2 weeks, he stood there going, spiral, spiral, elliptical, elliptical, spiral. Kevin quickly proved that he was better than a computer at doing this. So compared to what was available at the time, Kevin was much better at classifying galaxies. than any automated routine. But he also proved to his satisfaction and eventually ours that no student should be forced to look at more than 50,000 galaxies. But the project I had in mind needed the other 950,000 to be classified. And so we came up with this idea to ask for help. I grew up in astronomical societies. I knew that there were people out there who would be willing to spend time thinking about astronomy. And there'd been a couple of trial projects on a similar line, one of which involved looking at dust grains. And so we created this website, Galaxy Zoo, and said, okay, the idea is that I will give a talk. 50 of you will be inspired immensely by this discussion. We'll go home, we'll classify 50 galaxies, we'll repeat, and we thought in 5 years we'd have the million galaxies sorted. Turns out the internet doesn't work like that, as I suspect your fearless leader has now understood. Things that happen either slowly or very, very rapidly. And within a day, Galaxy Zoo was receiving more than 50,000 classifications an hour via this website, where people could tell us whether a galaxy was elliptical or spiral. If it's spiral, we want to know which way the arms were going. If you want to know why we did that, ask me afterwards. And then there was a button for merger and star. And the results were really good because we had lots of people looking at each galaxy. The crowd were actually more effective than Kevin, the single student who'd been classified. Because not only Kevin, bless him, made some mistakes, as you would if you spent 2 weeks just classifying galaxies, but because we had 30, 40 people look at each one, it doesn't matter if one person makes a mistake on a particular galaxy. But also I could understand which galaxies were truly difficult. So I could tell the difference between a galaxy where 20 out of 20 people say it's a spiral from one where 16 out of 20 say it's a spiral. And that turns out to be really, really useful. So Galaxy Zoo was this enormous success, and it taught us that there was a crowd of people out there who were willing to help. And were this a different talk, I could tell you about all the things we've discovered with Galaxy Zoo. What I'll do instead is I think I might just tell you about one result, because I want to prove that proper science comes out of this. And I could stack up, we've published about 100 papers, and about 500 different research papers use results provided by volunteers in Galaxy Zoo. But instead, let me tell you about one of my favorite mysteries. So here's a schematic of the Milky Way, a galaxy that delightfully has a bar at the center and then 2 or 4 arms, depending on how you count the scraggly bits. And the mystery in the Milky Way occurs deep at its center. And perhaps you know that we've got good evidence that there is a black hole at the center of the Milky Way. This is an image, or reconstructed image, of the center of the galaxy. And each dot you can see here is a star that over more than a decade has been traced orbiting around the center of the galaxy. And because we roughly understand stars, so we know what the mass of these stars are, so we can work out that they're orbiting something which has a mass of about 3 to 4 million times the mass of the sun. Interestingly, that number keeps going up slightly, but for our purposes, let's just say 3 million times the mass of the sun. And we know that that mass is crammed into a volume that's smaller than the solar system. And so physics, plus the fact there's not much visible there, again, the star-shaped thing has been added later, we know that this is really good evidence that there's a black hole at the center of the galaxy. We also know that most galaxies, if not all, have black holes at their center. You'll remember, for example, this image reconstructed from data from the Event Horizon Telescope of what I've been calling the luckiest light in the universe. So light that's seen escaping from the region around the black hole at the center of the galaxy M87, at the heart of the Virgo cluster. And through many different means, here's another view of M87, where you can see there's a jet of material being driven away from that region around the black hole. But from many different means, astronomers have been able to measure the mass of these black holes. And we know the mass of the galaxies because we can see how much light they're giving off. So we know at least how much mass there is in the form of stars. And it turns out there's a fundamental rule, which round here is known as the Megorian relation, after my colleague John Megorian, who's one of the people who established it. I think having a relation named after you is almost as good as having a comet named after you. Maybe it's better than having a faint comet. Anyway, the Megorian relation is this really simple rule because astronomy is a simple science. The Megorian relation says that the more massive a galaxy, the more massive a black hole at its center. So very roughly, M87 is about 100 times more massive than the Milky Way, and its black hole is about 100 times more massive than the black hole at the center of the Milky Way. So that's the rule that I'm talking about. And what I like about this problem is that that seems like common sense, right? That these two things are linked in some way. But actually, there's a profound mystery here. The Milky Way's black hole is only 4 million times the mass of the sun. But the Milky Way, just in stars, weighs a couple of 100 billion times the mass of the sun. And so it's quite strange that this black hole, which is relatively small, it's less than 0.1% of the entire, well, yeah, much less than 0.1% of the entire mass of the Milky Way. It's quite strange that it knows in inverted commas how big it should be compared to the rest of the galaxy. That there's this conspiracy that wherever you form one of these galactic black holes, it forms at the right mass to fit in the right galaxy. And so this requires explanation. And one of the nice ideas is that you need a way for the galaxy and the black hole to grow together. And you could do that if galaxies grow by merging. So you know perhaps that Andromeda, our nearest big galaxy, is going to merge with the Milky Way. That when that happens, the new galaxy, which some of my colleagues insist on calling Milkdromeda for some reason. Anyway, Milkdromeda will be a new galaxy that's about double the size of the Milky Way. And eventually the black holes that previously were in the middle of the Milky Way and Andromeda, they will merge too. And so you sort of double the size of the black hole. So as long as galaxies only grow by merging, you can explain this. What we hadn't been able to do was test this idea until two colleagues of mine, Brooke Simmons, who's now in Lancaster, and Becky Smethurst, who is both here in Oxford, and Dr. Becky on YouTube, highly recommended, realized that using Galaxy Zoo, we could select these very special galaxies. And these are all galaxies where they have spiral arms, they're in a disk, but unlike the Milky Way, there's no bulge of stars at the center. So Patrick Moore used to describe galaxies as two fried eggs clapped back to back. You have the spiral arms and then you have the yolk, which is a bulge. And these galaxies are bulge-free. They're perfectly flat disks. And that means they've never had a merger. And so our theory predicted that these galaxies, they've never had mergers, so they shouldn't have grown big black holes. And Brooke, Becky, and I managed to prove that they had perfectly normal sized black holes. And so using Galaxy Zoo, we showed that whatever explains the Megorian relation, it's not this growth through mergers. Now, that's quite a lot of detailed astrophysics. So here is a picture of a penguin. Because one of the next things that happened, we did Galaxy Zoo, we did a project called Solar Storm Watch, looking at solar storms, we did Planet Hunters, which I mentioned at the start, but other scientists started coming to us and asking for help. So I have a friend who's a zoologist called Tom. Tom used to go to the Antarctic every year and literally visit the same research sites and stand there and count penguins. 1, 2, 3, 4, 5. It doesn't sound like a very thankful task, but nevertheless, I guess he got to go to the Antarctic. But then Tom realized he could leave cameras there, which could take pictures like this one every hour. And thus he could understand how his penguins behaved over the course of the whole year. Trouble is, these days, he still goes back to Antarctica every year. He replaces the car batteries that power the camera. He pulls the memory card out. He comes back to Oxford, but he comes back to Oxford every year with 8 million images of penguins. He can't count them all, so we created Penguin Watch, original name Penguin Hunters, as you can see from the design. And now hundreds of thousands of people, including some 5-year-olds, help Tom count his penguin. I'm pretty sure that's a rock that just got labeled, but what do I know? Anyway, this technique of collaborating with large numbers of people online can be applied to all sorts of things, not just astronomy. And so this is the Zooniverse. The collection of projects that we've built lives under the general name of the Zooniverse. And I think this way of working has a big part to play in astronomy's future. And I want to just finish in the last 5 minutes of the talk by explaining that, because it's true, as many of you will be thinking, that we started running these projects in 2007. The world has changed a lot since 2007. And one of the ways in which it's changed is that computer vision, the series of techniques we have for getting a computer to recognize what's in an image, has moved on in leaps and bounds. And so you might expect this sort of project, which involves putting images online, even in Planet Hunters, we're asking people to look at images of graphs and sort through them, to sort of become obsolete. And I don't think that's going to happen. And I don't think that's going to happen partly because of something called the Zorilla problem. So these are images from another of our non-astronomical projects. These are images from Snapshot Serengeti, which is a project that shows people motion-sensitive pictures from the Serengeti National Park. And you have to label them according to which of 50 animal species are present. So giraffes, lions, porcupines, zebras in this case. Even as an astronomer, I can do that. And this project is one where you might think, well, surely modern technology can recognize giraffes. And actually, that turns out to be true, but only because this project existed. So modern machine learning, the kind of techniques that you use to do pattern recognition, that you might use, for example, to find supernovae in a survey, depends on large training sets. So you have to spend a long time training a very stupid network by going, this is a giraffe. This isn't a giraffe. This is a giraffe. And how well your computer does will depend on how large a pile of pictures of giraffes I have to give the computer. So in this case, once we'd run the project, we could train a computer to find a giraffe. And these days, I can do giraffe estimation automatically. You give me any picture, my computer can tell you whether there are any giraffes in it or not. But the biologists are also interested in this thing. This is a Zorilla. It's a small skunk-like creature of which I had not heard before starting this project. And Zorillas appear in 1 in every 2.5 million images taken by the network. So we could run this project for a ridiculously long time, for the rest of my life. We still wouldn't have enough images of Zorillas to train a computer. And in astronomy, we have lots of Zorillas. This is not a real image. This is obviously a montage. But I mean that in the sense that almost uniquely in sciences that are dealing with large data sets, astronomers are really keen on understanding the universe through finding the unusual. The galaxies that Brooke Becky and I used for the study I told you about in Galaxy Zoo, well, we found 100 or so of those. But we started with 1 million galaxies. In most other contexts, that's just noise. You could throw those away. It doesn't matter if you mislabel the weird 100 or so galaxies, whereas that's where the scientific value is. Astronomers are very interested in objects that don't look like any other objects or things that misbehave. And an example is this one. If you saw The Last Sky at Night, you will have seen that we were allowed to the outside of the University of London Observatory. And it's in Mill Hill. It's in the middle of London. It's a fabulous place, but it's also the place where in 2014, a guy called Steve Fossey and a bunch of undergraduates who were waiting for pizza to arrive became the first to discover a supernova, a bright stellar explosion in the nearby and well-known galaxy M82, which they were only imaging because that's where the gap in the clouds were. But Steve saw an image, and this isn't the discovery image, this is a follow-up, but Steve saw the image of M82 appear on the screen, and he knew the galaxy well enough to notice that there was a star where there should be no star, and they were the first to report the supernova. The thing is, more than 10 automated searches for supernovae had already taken pictures of M82 and detected the supernova. But in all the cases, the machine was surprised but not interested by this. All of these surveys did automatic hunting for supernovae, and the machine had accidentally learned that anything this bright tended not to be real. And so these were thrown away, and it was left for human inspection to find. So one way in which these projects will survive is that we will increasingly need people to help us look for the weird and the wonderful. And we might use machines to filter. So we'll get the computers to deal with the everyday and the boring, and then we'll share with as many people as we can online the unusual and the interesting. However, there's actually something a bit more profound going on. We've run projects called supernova hunters, which use data from pan-stars, and these days a telescope in California called ZTF, if you're Californian. And we've shown in these projects that the combination of having a computer look at your data and having people look outperforms either on its own. And so the combination of volunteers online plus a powerful computer sorting through data works much better than either on their own. So we get better results when we share our data and when we collaborate. And that's what we're doing across the Zooniverse. We're building projects that classify with people and computers. And in fact, if you go to Galaxy Zoo today, there's this little button that says Enhanced, and that will show you images that are selected by our computer, where the computer thinks that it needs your help to classify. And we found that this is much more efficient, which is probably just as well, because I think we've got about 2 years to get this right. This is the top of a mountaintop in Chile. This is now a photo that's nearly a year out of date of the enclosure, which will hold what's now called the Vera Rubin Observatory, which is going to be host to a survey called LSST. And the LSST survey is like nothing else we've ever had. It involves a telescope that's as big as the biggest telescopes in the world today. It's an 8.4 meter mirror, but it's optimized for a wide field of view. And though the details are still being argued about, roughly it will scan the whole sky every 3 nights. One of the things we'll do with that is build up the deepest images of the southern sky we've ever had, but the system will also look for changes in the sky, and it will issue a stream of alerts every time it thinks something has changed since the last visit. And we don't know, because no one's done this with an 8.4 meter or a camera this sensitive before, but we think that a reasonably conservative guess is that LSST will issue about 10 million alerts a night. And in there will be asteroids and Kuiper Belt objects and comets and variable stars and the flickering of AGN and exoplanets transiting their stars and all sorts of wonders. And all over the world, there are astronomers who are working out how to find within that fire hose of data more of their favorite objects: supernovae 1A, RR Lyrae variables, Kuiper Belt objects out near Pluto. But I am sure that in there will be the completely unexpected and unusual, and we will need help from volunteers online in the Zooniverse to be able to discover them. So we are working on this right now. We're working with the team at LSST to enable anyone in the world to get access to their data and to provide help. So thank you very much for listening. As you can tell, I've been having a lot of fun. Here is the blatant plug for the book, but I'm happy to answer questions about Zooniverse, about anything I've said, or indeed about almost anything else. Thank you very much.
Fabulous. Thanks very much, Chris, for giving your time today and giving us an excellent talk on these citizen science that we can all take part in. A lot of us have got plenty of time these days. I'm just hoping that some of these surveys miss some comets that some amateur can bag for themselves and get a proper name.
Don't worry, it's southern, so you're okay. And LSST will throw out anything that's bright, that's very bright. So the spectacular comets will continue to be discovered by amateurs for the most part.
Great stuff.